Welcome to the third lecture in our natural disasters course, in which we will be discussing earthquake geology and seismology. On the maps we see in this first slide, we have what we can all recognize as New England and part of New York. The red dots correspond to locations of earthquakes, and the size of the red dot, its diameter, is scaled to this to the size of the earthquake, the magnitude of the earthquake. We have two different figures. The one on the left showing those earthquakes that occurred between the years of 1924 and 1974, and the figure on the right, those that occurred between the years of 1975 and 2006. Most people don't think of New England as having earthquakes, but it does, just not very large ones, and so it doesn't have the level of infamy or notoriety that the West Coast of the United States does. But it does have earthquakes, and sometimes it does have fairly large earthquakes. Nothing that's extremely devastating, but enough to make its presence known. But so I kind of wanted to start with this slide to show that earthquakes do occur almost everywhere on Earth. They are not a phenomenon that is relegated to certain sections of the planet, as some may think. So an example of a very devastating earthquake was the Lisbon earthquake of 1755. So on the morning of November 1st, which in the Catholic Church, November 1st is a holy day of obligation. It's All Saints' Day, where the faithful attend Mass. And so on that morning, the Catholics of Portugal, which there are a lot of Catholics in Portugal, were all attending Mass. And there was two large earthquakes in close succession. And so you can imagine a lot of these stone structures, churches, they did not fare very well during the earthquakes, and they failed. There was also widespread fires, and the second earthquake caused sea waves, which we'll learn are actually called tsunami, that swept many people away. A few hours later, Lisbon was shaken again by an earthquake in Morocco, Fez, Morocco, and after all was said and done, about 70,000 people were killed, and 90% of the structures were destroyed or damaged. Now, the really tough part about this event is after the earthquake, well, at least after the first one, to escape the danger of the collapsing buildings and the fire, people went to the coastline, which made sense. However, the sea waves that were induced by the second earthquake came and swept them away while along the coastline. So it's very unfortunate. And I start with this because an event like this likely would not happen today. At least it should not happen today, because we know better. We know what type of structures to build in regions that have a large earthquake hazard, and we know the peripheral hazards of earthquakes, such as tsunami as well. So people should not go to the coastline, at least if they're properly educated. So something like this in 1755, these were deaths due to natural disasters due to ignorance, which hopefully are avoidable, should be avoided today. So what is an earthquake? An earthquake is an event in which the earth quakes, as its name may suggest, and vibrations are felt or recorded in the process of earthquake. So earthquakes can be caused by several phenomena. The most common is the movement of Earth across a fault, which a fault, as we'll discuss at the very bottom, it's a fracture in the Earth's surface, or not necessarily just in the surface, but in the rock near the surface. So volcanic activity could cause earthquakes, meteorite impacts, undersea landslides, and explosions of nuclear weapons. And the most common earthquakes, as we said, occur along faults. And faults are fractures in the outer layer of the earth, the lithosphere, in which the rock slides along these fractures, these faults. So to understand why earthquakes occur along faults, we first must understand the concepts of stress and strain. You may have heard of these words before, maybe in different contexts. But stress and strain are terms in physics and engineering. A stress is a force basically applied, in particular, a force applied to an area, but it's a force. And in this situation, the case of earthquakes, the force is being generated by the motion of the tectonic plates, and those tectonic plates are being moved by the mantle convecting beneath them. And the motion of these plates which generates stress, results in what's known as strain. And strain is a deformation or a change in shape. So strain is a gradual change in shape in order to accommodate the stress. And we said there's different ways in which materials can deform. There is elastic, ductile, and brittle. If the material undergoes elastic deformation, then as it deforms, as strain, what's said to accumulate, as that strain accumulates or as it deforms, energy in the form of elastic potential energy is stored in the material. So stress, as we said, stress in this situation is the force causing the deformation of the plates / rock, which is ultimately comes from the mantle convecting. And the strain is the deformation that develops in the plates / rock. And in this deformation or strain, elastic potential energy is stored. So think of when you stretch a rubber band, you are applying a stress to it. You are stretching it. You're applying a force and stretching it. That's the stress. Well, as a result, the rubber band accumulates a strain. It deforms, it stretches. And because that strain or deformation is elastic potential energy is stored in it. And that if you let go of that rubber band, that energy is released and it snaps back. When you think of a slingshot, you put a projectile in a slingshot and you pull it back. You are applying a stress to the rubber band. The rubber band undergoes a deformation, an elastic strain, and it stores energy, elastic potential energy. When you let go of it, the elastic potential energy is released. So that stored energy is released. In the case of a slingshot, it's transferred into the projectile and it launches the projectile. So whenever stress deforms an object and the object undergoes elastic deformation or elastic strain, energy is stored up in it. That's very important, the fact that energy is stored in it. So as the plates, they're moving, at the plate boundaries, that we find faults, the plates are moving in different directions. And because the plates are moving in different directions, the rock deforms around the fault. So as you can see here, this rock is moving. Oh, my pen doesn't seem to be working. This rock is moving this way, while this rock, oh, I'm on the wrong slide. This rock is moving this way, while this rock is moving this way. And you can see how this rock was originally undeformed. As a result of this motion, the rock is deformed, it changes shape. Now this process of the stress causing the rock to deform, it takes a long time. So this phenomenon occurs over the time scale of tens to hundreds of years. And as the rock slowly deforms, it is storing elastic potential energy. But why does the rock deform? And why is this strain allowed to build up? Why does the rock just not simply slide past each other along the fault? Well, the rock is not able to slide along the fault because the two sides of the fault, the rock on both sides of the fault, are locked together by friction. And that friction, which is a force, holds the two faces of the fault together, which results in the rock having to deform. And so strain will continue to build and accumulate, and therefore energy will continue to accumulate as long as friction is strong enough to hold the two faces of rock together. What do you think happens when the friction is no longer strong enough to hold the rock together along the fault? Well, all that energy that has been stored in the form of elastic potential energy is released as the rock quickly and suddenly snaps back to its original shape in a process known as elastic rebound. So the rock that's deformed, so this rock is going to want to snap back this way, this rock is going to want to snap back that way. And as it does, it returns its original shape. All that stored energy is released, and the energy travels through the earth in the form of vibrations, as we'll learn, known as seismic waves. So this is very similar to you stretching a rubber band, and eventually you stretch it so much that you can no longer hold it with your fingers. It slips through your fingers. Friction between your fingers and the rubber band is no longer strong enough to hold it in between your fingers. It slips out and snaps back. And so where the process for the rock to deform and accumulate all that energy took tens to hundreds of years, this process of elastic rebound, where the fault slips and the rock returns to its original shape and all that stored elastic potential energy is released, that process takes seconds to a few minutes. And so what took a very long time to store all the energy, all the energy is released in a very short period of time, resulting in an earthquake. So this process is called stick-slip motion because the fault is stuck together due to friction, and then eventually it slips. And then once the slip is over, then the process repeats itself. The thing is, how frequently the fault slips determines the size of the earthquake, right? Because if there's a lot of friction in the fault, then the rock won't slip very often. And as a result, large amounts of energy can accumulate because the rock will undergo a lot of deformation. And then finally, when the rock does slip, there'll be a large amount of energy to be released. So you have very infrequent but large earthquakes. Whereas if there is very little friction in the fault, then the fault ruptures or it slips very frequently. But because it's slipping very frequently, there was not a lot of time for significant amounts of energy to be stored. And so small amounts of energy are released. So you have very frequent small earthquakes. So the more friction, the longer the stick. The longer the stick, the bigger the slip. The bigger the slip, the larger the earthquake. Now this video illustrates this motion. So these are blocks resting on a surface. And these blocks are a physical model for this process of stick-slip motion. So where the block is in contact with the surface, that represents the fault. Now there's friction between those two surfaces that wants to hold the block in place. That's the friction in the fault. Now attached to each block is a spring, and attached to each spring is a string. It's hard to see the string. But in each of these, the string is going to be pulled at a constant rate. Now the pulling of that string is analogous to the motion on the plates. That's the stress. Now, as you pull the string, what happens is friction wants to hold the block in place. So if the block's not going to move, but the string is going to be pulled, something has to give, and that is the spring. The spring stretches. That's the deformation. That's the elastic strain. And as the spring stretches more and more energy is being stored in the spring until eventually the friction is not strong enough to hold the block in place anymore, and the block slips. And as it slips, all the energy in the spring is released, and it lurches. It just yanks the block forward. And that sudden motion of the rock or of the block generates the earthquake. That's the earthquake. So you can see there's 4 different blocks, and each of them have a different amount of mass sitting on top of them. That's to vary the amount of friction. So the more mass, the larger the weight, and the more friction. So there's the least amount of friction in the top block and the most amount of friction in the bottom block. So like we said in the previous slide, with very little friction, we expect very frequent but small slips, the top one. And for the more friction, we expect less frequent but larger slips, the bottom one. Let's see if that plays out as expected. See very frequent small slips for the top one. The bottom one slips less often. When it does slip, they're larger. We'll watch that one more time. If I can get it to replay. No, I guess not. Okay. Sorry, just dealing with YouTube. All right. So that's stick slip motion. So going back to faults, so how was a fault created? A fault was created by a process known as jointing, which is the brittle deformation of lithosphere rocks. Remember, brittle deformation is whenever it breaks, it cracks or fractures. So rock is deformed elastically in the lithosphere to a certain point, and then it will eventually break, which creates a fault. And so large stress differentials, which is forces in opposing directions on either side of a fracture or fault, results in the movement of rock in different directions along the fault. And so this movement can range from millimeters to hundreds of kilometers, resulting in the tilting or folding of layers. And to orient these faults, which are, you can imagine as surfaces or planes beneath the surface. Let's see, like this is a fault plane here. You can see that plane would extend back there. We use what's called the strike and the dip angle to orient the fault. So the strike angle is, so let's say this is the surface here, and this is the fault plane. This is the fracture right here, this plane. A little delay between my pen and my actions. I apologize for that. So the strike is the angle between due north and the line where the fault plane intersects the surface, which is this line right here. So the strike angle is this angle right there. So let's say if this line lined up with due north, the strike would be 0. If it was running east-west, the strike would be 90 degrees. where the dip angle is the angle in which the fault plane makes with the surface. And so it's this angle right here. That's the dip angle. So the dip angle can range anywhere from almost 0. That would be a very shallow dip. Fault plane would go down like that. Or it can go to 90, where the fault plane just goes straight down like that. So it'd be a 90-degree dip. So the dip angle is the angle measured between the surface and the fault plane. This is the angle right there. So the strike and the dip. Now we characterize faults mainly by the type of motion that occurs along them. And there's two main types. There's the first, which is the dip-slip fault. And so these faults have a dip usually around 45 degrees. So you can see how the fault plane is around 45-degree angle beneath the surface. And with dip-slip faults, the rock slides up or down. So it's in the direction of the dip. And the first type of dip-slip fault is what's known as a normal fault. And normal fault results from extensional or tensional stress where the rock is being pulled. And as a result of being pulled, the rock below slides up and the rock above slides down. Now we have better names for the rock below and the rock above that make it a little bit more easy to follow. And it's that if you can imagine yourself walking down this fault plane, and people did. Oh, lost all my drawings. And people did because people used to mine down faults, so they still do. And so the rock that you're walking on is called the footwall. That's the rock down here. And the rock that's hanging over your head is called a hanging wall. And so, I don't know whether my pen's acting all wonky. So in a normal fault, the footwall slides up while the hanging wall slides down. And that's the result of extensional or tensional stress. So we're going to find normal faulting around divergent plate boundaries where the rock is being pulled apart. So you can see an example of a normal fault here in this cutout on the roadside. You can tell because this layer of rock here, how it has been shifted. The footwall has slid up while the hanging wall has slid down. The other type of dip-slip fault is known as a reverse fault. And a reverse fault occurs under compressional stress where the rock is being pushed together. And the motion of a reverse fault is, well, the reverse of that of a normal fault. It's where the footwall slides down and the hanging wall slides up. And this overall results in a shortening of the rock, while the normal faulting, I forgot to mention, results in a extension or lengthening of the rock, where reverse faulting results in a shortening of the rock. Here you can see an example of a reverse fault. You can see how this layer, this has been shifted up, hanging wall shifted up, or the footwall slid down. That was not likely one earthquake, that was maybe several earthquakes that eventually, these layers probably started right there. And after one earthquake, it maybe slid up a little bit, slid down a little bit, another earthquake. So this has probably been many earthquakes to result in this offset in those layers. So we have dip-slip faults, which include normal faults, which result from extensional or tensional stress, and reverse faults, which result from compressional stress. Forgot to mention that we'd expect to find reverse faulting near convergent plate boundaries, where the rock is being pushed together. Then we have the other type of fault, which is called a strike-slip fault. And a strike-slip fault is where the motion is along the strike. And unlike dip-slip faults, which tend to have dips around 45 degrees, strike-slip faults tend to have dips around 90 degrees. So the fault plane usually goes straight down into the ground. And so strike-slip faults are the result of shear stress, where the rock is sliding past each other. And so we tend to find these types of faults along transform plate boundaries. Now, this type of strike-slip fault in particular is called a right lateral because the right side is moving toward you. So if you imagine yourself standing here with 1 foot on one side, 1 foot on the other, the right side is moving towards you if you're facing that way. Even if you turned around and were facing this way, the right side, your right side still moves toward you. As this person is demonstrating, the rock on their right is moving toward them, the rock on the left is moving away from them. If they would turn around, they would still experience the same thing. The rock on their right is moving towards them, the rock on their left is moving away from them. It's called a right lateral. And the other type of strike-slip fault is just the opposite sense of motion, left lateral, where the left side moves towards you and the right side moves away from you. Here's some examples of the offset of rock due to motion along a strike-slip fault. So this fence used to be connected and probably ran down through here, and which each subsequent earthquake, this moved that way, and this on this side moved that way. And so you could see that this is a left lateral fault because the left side would move towards you, the right side moves away from you. And then here, another thing here is the fault line. So this side is moving this way, this side is moving this way. So this is a right lateral. Interesting thing is this road was once straight and it was built on the deformed rock going across the fault. Whenever the fault slipped, the rock returned to its original shape, which now results in the road appearing curved. But it's not that the road was originally curved, the road was straight. It was just built on curved or deformed rock. When the earthquake occurred, the rock returned to its original shape, therefore bending the road, which is really cool to see. And so, as I said, these strike-slip faults typically occur along transform plate boundaries where the plates slide past each other. And most transform plate boundaries are along are little connecting segments along divergent plate boundaries on the sea floor. But there are a few transform faults that are on land and are much larger, and they're fairly notorious for earthquakes. So faults are not just these simple cracks, they're flat surfaces. They are complex zones of breakage with irregularly shaped surfaces, and they're many miles wide and long. So the stress and strain, they build up along a fault until rupture occurs, which rupture is whenever friction is overcome and it begins to slip or slide. And this rupture occurs at the weakest point on the fault, where the friction is the weakest, and then it propagates along the fault surface. The point along the fault where the rupture occurs is known as the hypocenter. So if we see this figure here, the darker purple shaded plane, that's the fault. The lighter shaded region, that's the area of the fault that slipped. So not the entire fault slips, a certain region of it slips. Known as a rupture area. And where that rupture initially began is known as the hypocenter. And you see that in this case, the ruptured area reaches the surface. And so you can see you actually have some offset in the ground at the surface. But that's not necessarily the case for all earthquakes. Sometimes the ruptured area does not make it to the surface, and so there's actually no visible sign of the offset at the surface. So we said the location of where the rupture begins is known as the hypocenter. That is actually what we consider the location of the earthquake. For convenience, we project that location up to the surface and call that the epicenter of the earthquake. So the epicenter of the earthquake is not actually where the earthquake occurred, it's the point on Earth's surface directly above where the earthquake occurred. And a quick way to remember the difference between the two is that hypo, like in hypothermic, means below. And so hypocenter is the location below the surface. Epi means outside, like your epidermis, your outer layer of skin. And so the epicenter is the location of earthquake at the surface. So this process of rupture is never a simple one-off event either. Rupture actually is a series of events over a particular time period, either a week, or a couple weeks, or months, even years, where there are multiple slips, with the largest slip being referred to as the earthquake, or the main shock. There could be smaller slips or smaller earthquakes that precede the bigger earthquake of the sequence, the biggest earthquake of the sequence, the main shock. And those are known as foreshocks. It is impossible to identify an earthquake as a foreshock until a large earthquake has occurred, in which all those preceding earthquakes are then a priori considered to be foreshocks. Aftershocks, on the other hand, are easily identified. After a large earthquake, smaller earthquakes occur, and those earthquakes are known as aftershocks. There are not always foreshocks for all large earthquakes. Some large earthquakes occur with no small earthquakes preceding them, but there are almost always aftershocks. So when an earthquake occurs, the stored elastic potential energy is then released and travels through the earth, along its surface and through its interior, in the form of seismic waves. And there are two primary types of seismic waves: body waves, those waves that travel through the interior of the planet, and surface waves, those waves that travel along the surface alone. So body waves, they're faster than surface waves, and they have short periods, which corresponds to high frequencies. We'll discuss period and frequency later. And they are the most energetic, or you can think of most maybe powerful, if you want to think of it that way, near the hypocenter. And there are two types of body waves: P waves and S waves. And remember, body waves are those that travel through the body of the planet, or the interior of the planet. So the first type of body wave is a P wave. You can think of P for primary, and that it's the fastest of all waves. And after an earthquake, it is always the first wave to reach any location, hence primary. And they move as a push-pull wave through the rock. It's alternating pulses of compression and extension, like the waves moving through a slinky. And because a P wave is alternating regions of compressed and extended material, they can travel through any material that can be compressed or expanded, which is all three states of matter: solid, liquid, or gas. So P waves are very similar to acoustic or sound waves. Actually, if there is a large thunderclap, that sound can actually convert into a P wave once it hits the ground and begins to travel through the ground, turns into a P wave. So just as sound can travel through solid, liquid, or gas, so can P waves. Where the other type of body waves, S waves, think secondary, they are the second wave to reach any location after an earthquake. Unlike P waves, these waves exhibit transverse motion, which is a shearing or shaking of particles at right angles to the wave's direction. So think of a rope. So if you have a rope affixed to one end and you shake one end up and down, what happens is a wave like this travels through the rope. So you can see that the particles move up and down this way, perpendicular to the direction that the wave is traveling. Now, S waves, because they're transverse or shear waves, they can only travel through materials that want to hold a shape, therefore can be sheared. So they can only travel through solids. S waves cannot travel through liquids or gases. So those are the two types of body waves. Then we have surface waves. So surface waves, they travel near Earth's surface, and they're created by body waves interfering with each other along the surface. This type of interference is called constructive interference, and they create these waves that travel along the surface. So you can think of surface waves as nothing but a bunch of body waves traveling near the surface that are adding together to form these new types of waves. So there's two types of surface waves. The first of the two are called love waves. It's an interesting name for a seismic wave, named after the person that first mathematically showed how they exist in the Earth. So similar to the motion of an S wave, but they're side to side. Okay, so the motion in the side to side motion in the horizontal plane. So if this was the surface here, and a love wave was traveling in this direction, the Earth would shake back and forth in that direction. So it would oscillate like that. Right, so love waves, they travel faster than Rayleigh waves, which are the other type of surface waves we're going to discuss. And because love waves are a combination of S waves interacting with each other near the surface, they cannot travel through fluids, liquids, or gases such as air or water. So as alluded to, the second type of surface wave is a Rayleigh wave. A Rayleigh wave is so if this is the direction the wave is traveling, we have a P wave, which has back and forth motion, combined with a vertically polarized S wave, so up and down motion. And so together, that back and forth and up and down creates an elliptical motion. So the particle motion or ground motion of a Rayleigh wave is elliptical motion, similar to kind of waves on the surface of the ocean. And so as a Rayleigh wave moves past, it kind of feels like you're in a boat that's rolling with the waves. So more energy is released as Rayleigh waves when the earthquake hypocenter is close to the surface. So the Rayleigh waves are stronger the closer the hypocenter is to the surface, and they can travel great distances as love waves can. So we mentioned the terms frequency and period before. And I'm sure you've heard of at least frequency, and definitely the word period, but maybe in a different context. But they are related to each other. And frequency and period are used to quantify basically how many waves, the speed, it's not really the speed. Well, let me just define each of them independently. The frequency of a wave is how many waves pass by a particular point per second. Okay. So if 5 waves pass by a particular point in 1 second, that wave is said to have a frequency of 5 hertz. Hertz, Hz, are the units of frequency. And hertz is 1 over seconds. That's what a hertz is, 1 over seconds. So it's number of waves per second. And so it's 1 over seconds, and that's hertz. Right? So if something occurs at a frequency of 1 hertz, that means it's occurring once every second. If something occurs with a frequency of 1/2 hertz or 0.5 hertz, that means it's happening half a time every second. Therefore, it happens once every 2 seconds. Something has a frequency of 10 hertz, it's 10 times per second. Right? Where a period is the amount of time it takes for one wave to pass by. So if it takes a wave 10 seconds to pass by, that is a wave with a period of 10 seconds. So when we say a whole wave, we're talking about one full cycle. So a cycle is one full wave, and so we can break a wave into parts. So we have the tops, which are known as crests, and the bottom, which are known as troughs. And so from crest to crest, that's one whole wave cycle. Trough to trough, that's one whole wave cycle. Or we can go, going from trough to crest to going from trough to crest, that's one full wave cycle. See, these are all the same length, right? That's one full wave cycle. Now, the time it takes for one full wave cycle to pass by a fixed point, that is the period. And the number of wave cycles that pass by a particular point in 1 second is the frequency. So let's say if a wave has a period, which we use a capital letter T to represent a period, of 10 seconds, so it takes 10 seconds for one wave to pass by. Ask, what is the frequency of that wave? Well, how many waves are passing by in 1 second? Well, if it takes 10 whole seconds for one wave to pass by, after 1 second, only 1/10 of a wave has passed by. So the frequency would be 1 over 10 hertz. Right? Where if the period was 2 seconds, what would be the frequency? Well, it takes 2 seconds to pass by a particular point, then how many waves have passed by in 1 second? Well, only half of a wave. The frequency would be 1 over 2 hertz. So if you can see the relationship here, the frequency of a wave is equal to 1 over its period. And conversely, the period of a wave is equal to 1 over its frequency. So therefore, if we have a wave that has a frequency of 10 hertz, what is its period? Its period is 1 over 10 seconds. So it only takes 1/10 of a second for a wave to pass by. Because, well, its frequency is 10 hertz, that means 10 waves are passing by every second. So it only takes 1/10 of a second for one wave to pass by. That's frequency and period. And so as the higher the frequency is, the shorter the period, right? There's more waves passing by every second, so the amount of time it takes for one wave to pass by decreases. The smaller the frequency, the larger the period. If fewer waves are passing by every second, that means it takes a longer amount of time for one wave to pass by. So these attributes of frequency and period, they're applicable to any type of wave, not just seismic waves. Sound waves, electromagnetic waves, all types of waves. And seismologists, they record and analyze these seismic waves to determine where an earthquake occurred and how large it was. So waves are fundamental to music and seismology. There's a lot of similarities between sound waves and seismic waves. Similarities are the more high frequency wave, if it's a short path travel. What does that mean? Well, imagine a trombone. As you play a trombone and you pull the slide out, what you're doing is you're increasing the length of the tube in which the sound can resonate. And so you're creating a longer resonance chamber, which creates a longer or a longer period or lower frequency sound. So if you pull the slide out, it's lower frequency, longer period, where if you pull the slide in, you're decreasing the chamber in which the length of chamber in which air can resonate and generate sound. And so that shorter resonance chamber creates waves that have higher frequency or smaller periods. Just like the string guitar, right? If you play a string open, the string of the entire length vibrates and it creates a sound of a particular frequency or period. But if you put your finger down on the fretboard, what you do is you effectively shorten the length of the string that's allowed to vibrate, and that shortened length causes it to vibrate faster, therefore generate a higher frequency, lower period sound. The same thing is true with seismic waves. So if there is a large segment of the fault that ruptures, it's very long, it'll generate very low frequency, large period waves. But if it's a very short segment of the fault that ruptures, it'll generate very high frequency, small period seismic waves. Now, oftentimes in an earthquake, you'll have short segments rupture here, 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 and there, and long segments rupture in different parts. So you'll have combination being generated. But it's the same concept. And so how do we locate the source of an earthquake using seismic waves? Well, we know between the two body waves that P waves travel faster than S waves. On average, P waves travel about 1.7 times faster than S waves. And so since they both begin from the earthquake, these P and S waves, and travel out away from the earthquake, the further you are from the earthquake, the more distance the P wave gains on the S wave. And therefore, if you're recording these seismic waves, the further you are from the earthquake, the longer the period of time between the P and the S wave arrival would occur, the further you are from the earthquake. This is called the lag time. So one way of thinking about this is, let's say you have a race, right? Here's the starting line. You have two runners, runner P and runner S. You can guess which one's faster, right? The race starts, both runners start from the same location. That is the earthquake. As they run the race, the runner P, which is faster, gets increasingly further and further ahead of runner S. So if we were to record the time at which they arrive, say at this location A, runner P would arrive, then after some amount of time, runner S would arrive. And let's call that delta T A, where delta T is the arrival time of the S wave, which is going to be larger. It takes more time for the S wave to get there, minus the arrival time of the P wave, which is shorter because it gets there sooner. And then at location B, if we were to record the arrival times, the difference in time between the arrivals would be larger because P would get here faster, and then S would get here more slowly. And because by virtue of being further away from the starting point, the delay time between the P and S wave or runner's arrival at this location would be larger. And so this delay time between the P and the S wave, it is a function of distance. Okay, so if we plot this against distance, it's not exactly a line. It goes something like that. Okay, so here we see, here is the minutes after the start of the earthquake. So this is time, and this is distance from the earthquake. And the yellow line is the arrival time, how long it takes for the P wave to arrive at different distances away from the earthquake. While the green line is the arrival time of the S wave, how long it takes for the S wave to arrive at a particular distance away from earthquake. So if you look at the P and the S arrivals at a particular distance, this is the delay time. So the P wave will arrive after 10 minutes at, say, 7,000 kilometers from the earthquake, but the S wave won't arrive until close to 20 minutes. It'll take 10 additional minutes for the S wave to arrive. And the closer you are to the earthquake, the shorter that delay will be. And it gets shorter and shorter the closer to the earthquake, and the further you are from the earthquake, the longer that delay gets. So if we can measure that delay time, that delta T, we can find how far away we are from the earthquake. That's only some of the information. All right, let's say that, we recorded these seismic waves and we found that the S wave arrived 11 minutes after the P wave. Well, that corresponds to roughly 9,000 kilometers. The earthquake occurred 9,000 kilometers away from this location in which we recorded these seismic waves. So let's say, this is where we recorded the seismic waves. Well, now the earthquake could have occurred anywhere along this circle whose radius is 9,000 kilometers. So we have an idea of where the earthquake could have occurred anywhere along the circle, but we don't know exactly where. We need more information. And so what information do we need? Well, we need the same information from 2 more seismograms. So we record the seismic waves after an earthquake at 3 different locations. We measure the delay time between the P wave and the S wave. That gives us a corresponding distance. We plot a circle on the map with the appropriate radius, and we do that for 2 other locations, and we'll get 3 circles. And those 3 circles will overlap at exactly 1 point. And that 1 point is the appropriate distance from all 3 locations and is therefore the location of the earthquake. Now, if we just had 2 circles, we would have 2 potential locations. We don't have a unique solution. So you need 3 seismograms, you need 3 recordings to figure out where the earthquake occurred. And this gives us the epicenter as well. And this method is called triangulation. It's not something unique to seismology. This is how your phone location is determined without using GPS. It communicates with 3 different cell phone towers. And so the cell phone tower sends out a ping in the form of a radio wave in all directions. Your phone picks up that ping and it sends a ping back to the cell phone tower. And what the cell phone tower does is it pays attention to the amount of time it took between the transmission of that ping and the reception of the response. And using the speed of light, they can calculate in the amount of time between the departure and arrival of those pings. It can be calculated how far away your phone is from that tower. And so then you draw a circle around that tower of the appropriate distance. And you do the same thing for 2 more cell phone towers. And those 3 circles will overlap at 1 location, and that's the location of your cell phone. Now, GPS does the same thing, except you're communicating with satellites in space and not cell phone towers, but you still need at least 3 satellites in order to triangulate your location. And by the way, this process is all automated. So once an earthquake occurs, computers have been programmed to recognize P and S wave arrivals. They measure the delay time and they do this for a bunch of different locations or recording seismic waves, and they triangulate the location of earthquake very quickly. That's how we know where these earthquakes occurred so quickly after they actually happened. So next, looking at the magnitude of an earthquake, the size of an earthquake, we used to use what's called the Richter scale. And the Richter scale is based off of the amplitude or the size of the seismic wave produced. And according to in the Richter scale, for every 10-fold increase in amplitude or 10-fold increase in the amount of shaking, the Richter magnitude would increase by 1. Now this is what's called a logarithmic scale. Using more simplified numbers, let's say we had shaking that was 1 unit of shaking. So the ground moved up and down 1 unit of distance. And let's say that's a magnitude 1 on the Richter scale. Well, magnitude 2 earthquake on the Richter scale would be one in which the shaking moved the ground up and down 10 units. That'd be magnitude 2 on the Richter scale. Magnitude 3 on the Richter scale would be one where the ground moved up and down 100 units. So each increase of 1 on the Richter scale corresponds to a 10-fold increase in the amount of shaking. As far as energy released by the earthquake, each increase in Richter scale corresponds to roughly a 45-fold increase. So a magnitude 3 earthquake on Richter scale releases as much energy as roughly 45 magnitude 2s. And a magnitude 4 earthquake releases as much energy as roughly 45 magnitude 3 earthquakes, or 45 squared magnitude 2 earthquakes. So there's many more smaller earthquakes each year than large ones, but more than 90% of all energy released by earthquakes is from the few large earthquakes each year. So there's huge amounts of energy released by a small number of earthquakes each year. These tables show us the frequency of earthquakes of different size. And so we have going from largest at the top, this is the table on the left, to smallest on the bottom. And so we see for magnitude 8.5 and up, we have less than 1 a year, 0.3. So what does this mean? That means that one of these earthquakes occurs roughly once every 3 years, right? Because after 3 years, 0.3 adds up to 0.9, and that's close to 1, right? We have on average 1 earthquake between the magnitudes of 8 and 8.4 each year, 3, 7.5 to 7.9, 15, 7.7 to 7.4, 56 earthquakes between 6.6 and 6.9. You can see the general trend. The frequency, the number of earthquakes per year increases as the magnitude decreases. So where there's 3 million earthquakes between 0 and 1.9. So as we talked in our first lecture, this is that inverse relationship between magnitude and frequency. So, but however, the shaking that results from an earthquake, the size of the seismic waves, is somewhat subjective, and that's dependent to some extent on the material that the shaking is occurring and the seismic wave is traveling through, whether it be bedrock or loose unconsolidated material like sediment. So if we were to measure the size of the earthquake based upon the size of the seismic waves, that could be a subjective measurement and not objective. And in science, we like objectivity, not subjectivity. With that said, seismologists have adopted a new method of ranking or quantifying the size of an earthquake, and that's using what's called the moment magnitude scale. And so the moment magnitude scale is used by measuring the actual amount of elastic potential energy released during the rupture of your fault. That's calculated by using the rock's shear strength, which is basically how strong the friction was in the fault, multiplied by the rupture area of the fault, and that multiplied by the slip, the distance that the fault slipped. That gives us the moment magnitude. The moment magnitude scale loosely follows the Richter magnitude scale. What I mean by that is magnitude 3 earthquake on a moment magnitude scale is roughly magnitude 3 in Richter scale, but they don't line up exactly, but they're close. And this figure on the right shows us energy in units of ergs, which is a weird English unit of energy. And it's a logarithmic scale, so each tick is a 10-fold increase. So this is 10 to the 16th, And this is 10 times that, so it's 10 to the 17th. This is 10 times that, 10 to the 18th. So each of these is a tenfold increase. And this is the equivalent moment magnitude, okay, of an earthquake. So what does this mean? That a magnitude 4 earthquake releases as much energy, or approximately releases 10 to the 18 ergs. But what's interesting is we can see earthquakes are plotted as these notable earthquakes are plotted as these green circles, and other events are plotted as triangles or squares. The average tornado releases as much energy as roughly a 5.0 earthquake. The Hiroshima bomb, dropped in 1945, releases as much energy as approximately a magnitude 6 earthquake. A hurricane releases as much energy as a 7 and change earthquake. So the world's largest nuclear explosion was a little bit larger than 8.0. Here is the largest earthquake ever recorded, and magnitude 9.5, occurred off the coast of Chile in 1960. This is the amount of energy released by a hurricane, average hurricane, over the course of 10 days. This is annual U.S. energy consumption, which is about the same amount of energy that what a magnitude 10 earthquake would produce. Just to note that a magnitude 10 earthquake is theoretically impossible. There's no fault long enough that could rupture that would generate a magnitude 10 earthquake. But so this allows us to compare earthquake magnitude and energy release to other energetic processes. You see, the daily Earth's daily recipient solar energy is extremely large. There's so much energy received from the sun, more energy that's released than a hurricane over the course of 10 days. So that's why there's so much potential in using the sun's energy for our own energy needs. So, continue looking at magnitude earthquakes and foreshocks, the main shock, the main earthquake, and aftershocks. As we said, large earthquakes are not just a single event, but part of a series of earthquakes that occur over some period of time, weeks, months, or years. The largest earthquake in a series is the main shock or the main earthquake. The smaller ones precede it, foreshocks. Smaller ones follow it, aftershocks. A large event may be considered a main shock. However, if it's followed by an even larger earthquake, then that originally categorized main shock is now recategorized or reclassified as a foreshock, and a larger one is classified as the main shock. Now, the magnitude of the earthquake is proportional to the length of the fault. How long of segment of the fault ruptured during the earthquake. So a 100-meter long segment of the fault, if it ruptures, it generates roughly a magnitude 4 earthquake. Multiply that by 10, so 1,000 meters or a kilometer long section of the fault ruptures, that generates roughly a magnitude 5. Multiply that by 10, a 10-kilometer long segment of the fault ruptures, generates a magnitude 6. Multiply that by 10, a 100-kilometer long segment of fault ruptures, roughly magnitude 7 earthquake. So we need 1,000-kilometer long fault, roughly, to generate magnitude 8, and even bigger for 9. So we would need basically 100,000 kilometers of fault to rupture to generate a magnitude 10 earthquake, and that's just not possible because there's no faults on Earth that are that long or that large. But in general, the longer the segment of the fault ruptures, the larger the earthquake. So now looking at ground motion during an earthquake. When we build buildings, at least for most of history and in most areas, we build buildings to handle vertical forces. So forces acting straight down. And those forces being the weight of the building and its contents. Okay, so if the building is shaking vertically up and down, the structure is usually safe. However, if the ground moves horizontally side by side, it generates horizontal forces on the building, which most buildings aren't built to withstand. And so that can do massive damage to buildings. It's not just the motion itself. The ground could move a lot and cause little damage to the building if it's moving very slowly. What's the most damaging part of the motion is the acceleration, which the acceleration is how rapidly the ground changes speed or direction. So if the ground is shaking back and forth very rapidly, that's a large acceleration. When we measure the acceleration of ground motion during an earthquake in factors of the acceleration due to gravity, or G. So a building will suffer, weak buildings will suffer damage from horizontal accelerations of more than 1/10 of that due to gravity, so 0.1 G. At isolated locations, after large earthquakes, horizontal accelerations have been measured up to 1.8 Gs. So that's almost twice the acceleration due to gravity. That's a huge amount of acceleration. And that's extremely damaging. So periods of buildings and the response of their foundations are important to keep in mind too. So all objects that have finite mass, I should say all solids that have finite mass, they have natural frequencies in which they like to oscillate. And we know this is how we make musical instruments, right? You know, strings of different length vibrate at different natural frequencies. And what else? If we fill glasses up to different heights of water and we tap the glass, we generate different frequencies. And so for objects that are long, like a building is, it's taller, say if it's a tall building, its frequency is roughly a function of its height or its length. Just like the frequency at which a string vibrates is partly a function of its length. And so buildings, like all other objects, have natural frequencies or periods at which they want to oscillate, right? If you pluck a guitar string, it has a particular frequency at which it wants to vibrate. It'll vibrate at that frequency every time you pluck it. Just like if the ground begins to shake a building wants to oscillate or shake at a particular frequency or period. In general, the natural periods at which a building wants to sway or oscillate is about 1/10 of a second per story. In other words, if you had a 10-story tall building and the ground was moving, it'll sway back and forth. It'll take about 1 second for it to make one complete oscillation. So if this is a building and it sways, it sways back and forth this way. It take 1 second for it to go from here, there, here, and then back. If it was 10 stories tall. If it was 20 stories tall, it'll take roughly 2 seconds. So a 1-story house, it shakes at about 1.1 second per cycle. So that means it has a period of 0.1 seconds, which is 1/10, or a frequency of 10 seconds. It shakes back and forth 10 times every second. On the other hand, a 30-story building sways at about 3 seconds per cycle. So it's a period of 3 seconds. It takes 3 seconds for it to sway back and forth, and therefore it has a period frequency of 0.33 or 1/3 hertz. So the building height influences the frequency or period at which the building wants to oscillate. Also, the building materials influence it as well. Flexible materials such as wood or steel, they have longer periods of shaking. So if something's flexible, it doesn't oscillate as quickly. It has a slower frequency of oscillation, where more stiff, rigid materials like brick or concrete, they have higher frequencies at which they want to oscillate or shake at. Just like if you imagine a steel rod that's very thin and kind of flimsy, and if you strike it, it oscillates or shakes at a lower frequency. Where if it's a thicker, more rigid steel rod that's not as flexible, you strike it, it'll oscillate at a shorter period or higher frequency. So why we're talking about the frequency or period at which building wants to shake is because it's important that those frequencies and periods which the ground shake, the frequency or period at which the ground is shaking doesn't match the frequency or period in which the building wants to shake or oscillate. So when seismic waves pass from harder rock to softer rock, they slow down. And in order to carry the same amount of energy per unit time, their amplitude has to increase, which results in greater shaking. So we find this the shaking due to seismic waves is larger in softer rocks or unconsolidated material like sediment, sand, gravel, silt. The shaking is amplified. In consolidated harder material like bedrock, shaking is smaller. It's somewhat diminished. And so shaking tends to be stronger at sites where there's softer ground foundations, and we find those softer grounds in lower elevations where sediments accumulate, basins, valleys, reclaimed wetlands, etc. And if the period of the wave traveling through these materials matches the period of the building, the shaking is amplified in the building, and a process known as resonance occurs. And resonance is a common cause of catastrophic failure of buildings. I'll leave these 3 links here. These videos are in a supplemental video folder for this chapter, which you should check out. So it shows buildings in Tokyo oscillating back and forth after an earthquake, so you can see this process of buildings oscillating. You can see building resonance, where there's 3 different model structures on a platform that's shaking back and forth by an actuator. And the frequency of shaking is dialed up. And as it's dialed up, you can see that the frequency of shaking resonates or matches the frequency at which the buildings, which I forgot to mention, all 3 of them are 3 different heights, which they want to shake. And you can see it's fairly dramatic when the shaking of the platform is resonating with the building. The shaking of the building, the oscillating of the building, is amplified, what's called resonance. In the final video, it shows the destructive power of resonance, how the wind resonating with the Tacoma Narrows Bridge in Tacoma, Washington, which caused the resonance and caused the bridge's oscillations to amplify and eventually caused it to fail. So I encourage you to check out those videos. But basically, simplistically, you can get an idea of what resonance is by thinking about pushing a child on a swing. Right, the child swings at a particular frequency, right? How many swings per second, or they swing at a particular period, how long it takes for them to make one oscillation. In order to make them swing higher, you have to push them at a frequency that matches the frequency at which they are swinging, or at a period that matches the frequency at which which are swinging. And if you push them at the same frequency, what happens is they swing higher and higher and higher, because your pushing is resonating with their oscillating, and that's resonance and causes the oscillation to increase in amplitude. So the earthquake intensity, that's what we feel during an earthquake. It used to be, well, it still is, but it primarily used to be indicated by the Mercalli intensity scale. This was developed to quantify what people feel during an earthquake. It was primarily used for earthquakes before instrumentation, before we had seismometers to measure the seismic waves. And it's also used currently in areas where the earthquakes occur that we don't have instrumentation deployed. And the Mercalli intensity scale, it assesses the effects on people and buildings. So this is the magnitude of the earthquake in the left-hand column. And this is the corresponding Mercalli intensity scale. It goes from 1 to 2, 3, 4 to 5, 6 to 7, 8 to 9. Oh, sorry, 7 to 8, 9 to 10, and then 11 to 12. And this is a description of what those intensities, what sort of impact they have. This is the corresponding acceleration as a percent of G. And so magnitude 8 and up, that's a 10 to 12 on a Mercalli intensity scale. And that's where the acceleration is more than that due to gravity. So some variables in the Mercalli scale is the earthquake magnitude. The bigger the earthquake, the more likely there is to be death and damage, and therefore larger ranking on the Mercalli scale. Distance from the hypocenter, usually but not always, the closer you are to the earthquake, the more damage, higher the ranking on the Mercalli intensity scale. And finally, the type of rock or sediment, making up the ground surface. Hard rock foundations vibrate from nearby earthquake body waves. So the high frequency body waves, they tend to resonate with harder, more consolidated material bedrock, where soft sediments are amplified by distant earthquake surface waves. And so steep slopes can generate landslides when shaken as well. So more Mercalli scale variables. The building style, so body waves near the epicenter are amplified by rigid short buildings, because remember, body waves have higher frequencies than surface waves. So body waves are going to resonate with buildings that have higher natural frequencies, which are shorter, more rigid buildings. Where the lower frequency surface waves, they're going to be amplified or resonate with tall buildings, especially if they're on soft foundations. So basically the intensity of the shaking could be increased if it's because the body waves are strongest close to the epicenter. So if we have short rigid buildings on solid rock close to the epicenter, that'll intensify the shaking more. And if we have tall buildings built on soft material further away from the earthquake, those surface waves will resonate with those buildings and intensify the shaking as well. Where conversely, if we had tall, flexible buildings built on bedrock close to the earthquake, that would not generate a lot of shaking in the building. And if we had short, rigid earthquakes built on soft materials far from the earthquake, the surface waves would not resonate with those buildings, resulting in minimal shaking. And finally, we have the duration of the shaking. Obviously, the longer the shaking lasts, the more buildings will be damaged. So here's a case history of these Mercalli variables. This was an earthquake in 1971, the San Fernando Valley. Earthquake was a magnitude 6.6 with 35 magnitude or higher aftershocks and 7 minutes after the main shock. And so you can see these colors represent the different Mercalli scale rankings. So the highest is in the center. Then as you move away, the Mercalli intensity decreases, creating this bullseye damage pattern. Obviously, the shaking is the highest to center, and it decreases with distance away. You can see there's these little tongues out here. And these tongues are partly following where there's people that make observations, right? Building style is a factor, as we said. Soft first-story buildings were a major problem. Hollow core bricks at the Veterans Affairs Hospital caused collapse, and collapse of freeways and bridges were very destructive. So this soft first-story buildings, what that refers to, that's buildings that basically have a garage as the first floor. So it's not a very sturdy first floor, and they're very susceptible to collapsing. And the hollow core bricks, those are like those gray cinder blocks that are hollow. Where see this Mercalli scale intensity map doesn't have the same symmetric bullseye shape as the last one. This is the New Madrid earthquake that occurred in Missouri near the turn of the year 1811, 1812. It was a magnitude 8 earthquake, and aftershocks were felt for more than a year afterwards. So the earthquake was strong enough to ring church bells on the east coast of the United States. But you see how the Mercalli intensity scale, the pattern, it kind of, instead of being a symmetric circle bullseye, it kind of runs more oblong. And why is that? Because remember we said that soft sediments amplify the shaking. And in this fault, it runs along Mississippi River. So this is the Mississippi River Valley right here. So the Mississippi River runs along here, and so the shaking was amplified by these sediments in the Mississippi River. And then this is the Ohio River Valley. And so the shaking, it was intensified going up through the Ohio River Valley. So you can see how the shaking kind of reverberated up in these soft sediments that are deposited by the rivers in these valleys. And because the east coast of the United States isn't as fractured and mangled due to less recent tectonic activity as compared to the west coast of the United States, the seismic energy can travel through the ground more coherently without being scattered, so it can travel further without dissipating as much. And that's another reason why this earthquake was felt so much further away than the ones in California. So if we're going to build in a region that has a seismic hazard, when we build our buildings, we want to make sure that we're eliminating resonance. We do not want the frequency at which the ground is shaking to match the frequency at which the building wants to shake. So how do we eliminate resonance? Well, we can change the height of the building. We know that surface waves, long period surface waves, are amplified in soft materials. So if we're building in soft materials, like in the sediments in the valley, we want to build short, rigid buildings. We know that high frequency body waves are more prominent in harder consolidated materials like bedrock, and so we'd want to build taller, more flexible buildings in the bedrock. We can move the weight of the buildings, concentrate the weight towards the lower parts of the floor instead of higher in the building. The higher the weight is distributed in the building, the more it wants to shake. Change shapes of the buildings so they are broader at the bottom instead of just these rectangular objects, rectangular shapes. Change building materials. Flexible materials have more give, wood and steel, where concrete materials, brick, stone, they're not as forgiving. If they have any horizontal motion, they can crack and be compromised and fail. Change the attachment of the building to the foundation. We'll talk about this in a little bit. This is called base isolation. If we can somehow decouple the building from the ground so that the building doesn't necessarily, the base of the building doesn't necessarily have to shake at the same frequency which the ground is. And so, as I said earlier, if we have a hard foundation, we're going to have higher energy, higher frequency waves are going to be higher energy. So we want to build tall, flexible buildings. If we have soft foundations, such as sediments, the lower frequency vibrations are going to be more energetic. So we want to build shorter, stiffer buildings to avoid resonance. We could also build shear walls. So shear walls are designed, they're walls designed to be able to withstand horizontal forces on floors, roof trusses, and transmit those forces down into the ground. The lack of shear walls is typically causes structures like parking garages to fail. So a parking garage has these levels, but they only have these pillars that support the vertical stresses. There's no shear walls, or basically there's nothing to support horizontal stresses. So if you can build some horizontal supports in there that can support these horizontal stresses and transmit them down to the ground, you can prevent the building from collapsing. So here's a parking garage in California. You can see these angled members here are helping create horizontal strength. So it's almost like taking a house of cards, which has no horizontal strength, a light breeze could blow it over, and just reinforcing the cards, adding some tape, gives them some horizontal strength. So less likely to fail in the event of horizontal stress. So other ways we can create horizontal stress is using braced frames. So we have these cross bracing within the framing of the building, or buttressing the building, or we can even isolate the building from the ground completely. This is called base isolation. So say if we put the building on rollers, the ground shaking back and forth, the ground doesn't necessarily have to shake as frequency as the same as the ground, since it's on rollers. And there's different ways of base isolation, where you can put the building on pillars, and those pillars are then go down into the ground and are surrounded by these layers of rubber and steel. So as the ground shakes, the energy is absorbed. It's kind of like a cushion, and it dampens the shaking. So some of the, not all the energy is transmitted up to the building, so the building does not shake with the same vigor as the ground. So these are all techniques which we can use to build buildings that are more resistant to collapse during the event of an earthquake and seismic waves traveling through the area. And many regions of at least this country and other countries, developed countries, they have building codes in regions where there's seismic hazards, called seismic codes, in which buildings have to be built in order to withstand these horizontal stresses. And existing buildings need to be retrofitted. That's why whenever the 2010 Haitian earthquake occurred, it was so devastating to Haiti, because their infrastructure was not built to withstand horizontal shaking, so everything failed. Where if that same size earthquake were to occur, say in Tokyo or Santiago, Chile, or San Francisco, California, there would be much less damage, because the infrastructure is built to withstand those horizontal forces, and it's built to try to mitigate the amount of resonance. And so that's an example of how having the resources and having the government to make sure that the infrastructure is built in a way to mitigate the negative impacts of seismic waves on our infrastructure is important to save lives. One thing about earthquakes is that they themselves do not kill people. Imagine yourself standing in the middle of a large, wide open field, and an extremely large earthquake occurs. What is the worst thing that's going to happen to you? You're going to fall down. Maybe you sprain your wrist. At worst, you break it. You're not going to perish, though. Your life is in no significant peril. What does kill people in the event of earthquakes are buildings falling down, falling on their head. It's fires from water line, from gas lines breaking, electrical lines breaking, igniting the gas leaks, and then the water lines are broken, so the fires cannot be fought, and all the debris and rubble provide fuel from the fire. You have these widespread fires. It's the failure of infrastructure due to an earthquake that kills people. So once again, it's not earthquakes that kill people, it's the failure of infrastructure during an earthquake that kills people, or as a result of an earthquake that kills people. So let's say you find yourself in a region that has a significant seismic hazard, and you are unfortunate enough to experience a large earthquake. So, or let's say we're not there yet. Say you could experience a large earthquake. So what should you do prior to mitigate the effects of an earthquake? Well, inside and outside your home, you should visualize what might fall during strong shaking and anchor those objects by nailing, bracing, tying them, etc. Now, living on the East Coast, oftentimes when you buy furniture, I always found it odd whenever it comes with the anchoring supplies to anchor the bookcase or dresser to the wall. I mostly thought it's like, oh, this is to prevent a child from pulling it down on themselves. But it's also because those anchorings come in handy on the West Coast because they want to anchor their furniture to the wall, such as a bookshelf, a large, tall bookshelf, because they don't want that bookshelf to fall over on anyone in the event of an earthquake. So they want to anchor it to the wall. Anything that's hanging overhead, light fixtures, and so forth, I want to make sure that they are strongly anchored and they don't fail. Nothing's going to fall off the walls or fall from the ceiling. Inside and outside your home, you want to locate safe spots with protection. So protection from what? Protection from falling objects. So you want to get under a heavy table, a strong desk, under a bed, in a doorway. If you are in a doorway, it's very hard for something to fall on you because you're in a doorway. You want to make sure you stay away from any overhead glass, though. So that's before an earthquake. During an earthquake, you want to duck, cover, and hold. You want to stay calm. If inside, stay inside. If outside, stay outside. Do not go into or out of a building because it's on the outsides of buildings that often objects are falling from large heights and are very deadly. So you have a greater chance of being struck by those objects as you're entering or leaving a building. That's why it's best to not enter a building or leave a building during an earthquake. So this concludes our lecture on earthquake geology and seismology. Thank you very much.